Hello, my name is Bhaskar Krishnamachari. I'm going to talk today about dynamic curves for decentralized autonomous cryptocurrency exchanges. This is work co-authored with Feng and Eugenio Grippo at USC. So there's really an ongoing revolution happening in decentralized finance, in particular cryptocurrency exchanges that are built on top of what are called automated market makers. And two examples of such AMM based decentralized cryptocurrency exchanges are Uniswap and Curve. To give you an idea of how significant they are, Uniswap has reported that something like 44 million trades have taken place on this decentralized exchange with a total volume over all time of about $231 billion. And so when we look at how these decentralized cryptocurrency exchanges work, at the core of it is a function, let's say a function between two different tokens, y and x. And these functions can be of different types. For example, there may be a constant price token, which corresponds to, constant price exchange, which corresponds to the sum of x and y being kept constant. It could be a constant product curve, such as used in Uniswap, and this is shown in the purple dashed line. And another example is the invariant that's used in staple swap, and that's shown here in the blue solid curve. But essentially, all of these curves uh, give a particular form for the liquidity pool on the decentralized exchange that must always be maintained. And as these invariants are being maintained, traders can come to the liquidity pool and trade against it and put in tokens of type X and get back tokens of type Y or vice versa. So let's take a look at a little bit more detail of how that works. So here is an automated market maker curve. And we are initially at some point x comma y, which means that the liquidity pool consists of small x tokens of type X and small y tokens of type Y. A trader can now come to this pool, and if this trader were to offer the pool delta X tokens of type X, then we would have to be constrained to move on this curve to a new point that is denoted here by the red circle. And in this new point, the curve has delta y tokens less of token y than it did in the original point. And these delta y tokens will be given back to the trader. So the trader is essentially putting in delta x tokens and getting back delta y tokens from the pool. The pool in the other direction is gaining delta x tokens of token x and losing delta y tokens of token y. And so this trading is happening against the liquidity pool. It's helpful to define something called the pool price. This is the slope of the tangent curve at any given point of the liquidity pool. So for example, at the original point xy, we can see that the slope of this curve would be P1. And in general, the price of the token X in terms of number of Y tokens would be given by the negative derivative of the AMM curve at a given point. So Px at xy would be the negative derivative of y with respect to x. Another useful definition is the value of the liquidity pool at any given time. And again, we can measure this in terms of the y tokens as follows. We would say that the value of the liquidity pool at a certain price p is given as px times x plus y. So essentially, it's how many tokens there are of type x, what is the price of those tokens of type x, multiply those together, you get the total value in terms of x tokens, plus y is the value that is in the y token. So the sum of this is the total value of the pool. What we have is that we are able to also look at other properties of these AMM curves. For example, we're able to look at the slippage of the price on a given trade. So again, let's begin at some initial point. Let's say we begin at the point x0, y0. And in this case, the trader is going to come in and is going to want from the pool delta x tokens of type X, and in return has to give something back. Now, given the original price at the original point x0, y0, ideally the trader would have liked to pay that price to get delta y0, uh, or essentially to give delta y0 tokens in order to get the delta x tokens that he or she is interested in. However, because of the nature of this curve, what they will actually end up paying in order to get delta x tokens would be delta y tokens. And here we can see in this picture that delta y is bigger than delta y0. And the gap between these two, the amount that they have to pay to get delta x tokens and the amount they would have paid had the price remained constant, is called slippage loss. And so delta y minus delta y0 here is the loss that the trader is incurring. And generally, the slippage loss is going to be larger for larger trades. Another property of AMM curves is that in general, the pool price will change after every trade. So if we were at some original point xy and move to a new point x plus delta x and y minus delta y, we're going to end up with a different price P2 than we had originally, because the slope of the line that's tangent to the curve is going to be different at the new point. So given that there's going to be a change in pool prices, a change in the XY holdings whenever a trade happens, we can expect that the value of the liquidity pool will change after a trade. And this also can be defined and measured by something called the divergence loss, which is essentially the change in value normalized by the value of the original point. After a trade, the value has changed compared to what it was to begin with. And looking at the sort of percentage change in value, or ratio change in value, is referred to as divergence loss. And it can be shown, for example, for the constant product curve, that this divergence loss is given by an expression as shown here on the slide. And really that this divergence loss is going to be a negative quantity, meaning that you've essentially lost value after a trade. And you lose value no matter what size trade you make, so long as it's non-zero, whether or not you buy or sell the token X in that trade. And the amount of the loss is still a function of the size of the trade that you make. In our paper, we examine a particular issue that AMMs face, and that is that if the liquidity pool of that automated market maker is small compared to the overall market, then the pool price after a trade is likely to be quite different from the market price. And so this gap between the market price and the pool price attracts arbitrageurs to the market, and these arbitrageurs are going to effectively drain resources from liquidity providers. And that's not, in general, a good thing, because these liquidity providers are the ones that are actually funding the operation of the AMM. And so what we do in this paper is to propose a solution to this problem, which involves using an oracle to correct the price curves automatically and change them based on the current market price. So this is how the approach works. Let's say that we have a given AMM curve. We're at an initial point xy, a trade takes place, and we're at a new point. Instead of keeping with the old curve as we would in a typical constant AMM exchange, we propose instead to actually change dynamically the curve to a new curve. In particular, the new curve shown here in purple is going to be passing through the new point, and it's going to maintain a slope at the new point that is the same as the slope of the curve, of the tangent to the curve in the original point, and thus effectively the pool price is not changing, even though the trade has taken place. And this is done essentially to match the pool price to the market price. And specifically, we propose in our paper a concrete family of dynamic curves that can be used to generalize the constant product curve that is used, for example, in Uniswap. And it takes the form that is shown here: y of t equals k over w of t divided by x of t minus a of t, where w of t and a of t are new parameters that we introduce to allow for these dynamic changes of the curves. And in particular, if we apply the equations that are given on the slide, in particular adapting a of t and w of t to the current market price, then we can ensure that the new curve satisfies the property that it passes through the value of the liquidity pool at the current time, and its slope will be equal to the market price at the operating point. So we're able to show that in such a dynamic AMM, because now the market price and the pool price are always equal, there is no arbitrage. And now that there is no arbitrage, it turns out that the liquidity providers are able to do a lot better. And in particular, if we have a family of monotonically decreasing curves that are strictly convex, we can show that at every trade, the trader is going to experience a slippage loss, and the corresponding amount that they lose is going to be accrued as value to the liquidity providers. Of course, the traders may not incur a lot of loss on each trade if they're relatively small compared to the size of the pool. But the point is here that the liquidity providers are actually gaining from helping to fund the operation of the AMM. And in particular, they're not losing out because of the arbitrage that happens in a static AMM model. We present in the paper a number of simulations. We show simulations, for example, of the static constant product AMM on this slide. And we can see that in the simulation, as can be seen in figure E, the market price is increasing steadily through the simulation time. And at some point, this market price gets so large compared to the pool price that, in fact, there's essentially very limited further trading. The pool price gets more or less saturated at a certain value. And this happens at a point that the arbitrager in our simulation essentially runs out of Y tokens to continue arbitraging. But the effect of the arbitrager is to reduce the value overall of the liquidity pool, as can be seen in figure C here. The value for the liquidity provider is actually lower after some time than it was at the beginning of the simulation. And this also affects how much fees the liquidity providers are able to collect, and so on. In contrast with the dynamic constant product AMM curve, there is no arbitrage opportunity. We can see that in our simulations, the market price and the pool price are always matching each other. There is a benefit overall to the liquidity provider in this simulation compared to the case with the static AMM. They're able to retain and possibly even increase the value of the pool over time due to the gains obtained from the slippage losses of the traders. So in conclusion, we've presented a new dynamic curve-based automated market maker approach that can be used in decentralized exchanges that has the benefit that it eliminates arbitrage and benefits the liquidity providers. This work opens up a number of avenues for future work, including how would you actually implement such a dynamic AMM? It requires an oracle, and to study the impact of delays and errors in such a price oracle on the performance of the dynamic AMM would be a topic of interest. We have presented a specific family of dynamic AMM that are generalizing the constant product curve. This could be extended to other families of dynamic AMM as well. And we would also like in future work to explore certain path dependence properties that these dynamic AMMs have, and solutions potentially to address any concerns that might arise from that. With that, I'd like to conclude my presentation, and thank you very much for your time in attending to it. Thank you.